In previous video, I discussed factor analysis part 1. In this video, we will discuss in further. I gave the name of factor analysis part 2. We will discuss in further analysis versus component analysis. What is that? With the basic of understanding of how variance can be partitioned, the researcher is ready to address the difference between the two methods known as common factor analysis and component analysis. The selection of one method over the other is based on two criteria. The first is that the objective of the factor analysis, and the second is that the amount of prior knowledge amount, the variance in the variable. Component analysis is used to when the objective is to summarize most of the original information in a maximum number of factors to prediction purpose. In contrast, common factor analysis is used primarily to identify underlying factor or dimensions that reflect what the variable shared and common. The most direct comparison between the two methods is by their use of the explained versus explained variance. Component analysis, also known as a principal components analysis, consider the total variance and the drive factor that contain small proportions of unique variance and in some instances error variance. However, the first few factors do not contain enough unique or error variance to distort the overall factor structure. Specifically, with component analysis, unities value of 1.0 are inserted in the diagonal of the correlation matrix so that the full variance is brought into the factor matrix. Figure 5 portray the use of the total variance, and here is the figure 5. Here is a diagonal value, variance, unity, total variance, commonality, common, specify, and error, variance extracted. Here is a variance extracted and variance excluded. Let's talk about the common factor analysis. In contrast, considers only the common or shared variance, assuming that both the unique and error variance are not of interest in defining the structure of the variable. To employ common variance in the estimation of the factors, commonality instead of unities are inserted in the diagonal. Those factors resulting from common factor analysis are based only on the common variance. As shown in the figure 5, common factor analysis excluded a portion of the variance included in a component analysis. How is the researcher to choose between the two methods? First, the common factor and component analysis model are both widely used as a practical method. If we talk about as a practical matter, the component model is the typical default method of the most statistical program when performing factor analysis. Beyond the program default, distinct instances indicate which of the two method is most appropriate. Component factor analysis is most appropriate when data reduction is a primary concern, focusing on the minimum number of factors needed to account for the maximum portion of the total variance representing in the original set of variable, and the prior knowledge suggests that specify and error variance represent a relatively small proportion of the total variance. Common factor analysis. Common factor analysis is most appropriate when the primary objective is to identify the latent dimensions or constructs represented in the original variable, and the researcher has little knowledge about the amount of specify and error variance and therefore wishes to eliminate this variance. How do we decide on the number of factor to extract? Criteria for the number of factor extract. So both factor analysis method are interested in the basic linear combination of variables in the sense that the particular combination of original variables account for more of the variance in the data as whole than any other linear combination of variables. Therefore, the first factor may be viewed as the single best summary of linear relationship exhibited in the data. The second factor is defined as the second best linear combination of variables subject to the constraint that it is orthogonal to the final function to be orthogonal to the first factor. The second factor must be derived from the variance remaining after the first factor has been extracted. Thus, the second factor may be defined as the linear combination of variables that accounts for the most variance that is still unexplained after the effects of the first factor has been removed from the data. The process continue extracting factor accounting for smaller and smaller amount of variance until all of the variance is explained. For example, the component method actually extract the factor where is the number of variables in the analysis. Those in 30 variables are in the analysis, 30 factors are extracted. So what is gained by factor analysis? Although our example contain 30 factors, a few of the first factor can represent a sub, substantial portion of the total variance across all the variable. Hopefully, the researcher can retain or use only a small number of the variables and still adequately represent the entire set of variables. Thus, the key question is how many factors to extract or retain. In deciding when to stop factoring, that is, how many factors to extended, the researcher must combine a conceptual foundation, how many factors should be in the structure, with some empirical evidence, how many factors can be reasonably supported. The researcher generally began with some predetermined criteria such as the journal number of factor plus some journal threshold or practical reveals that, for example, required percentage of variance explained. These criteria are combined with empirical measurement of the factor structure and extract quantitative basic for deciding the number of factor to extract has not been developed. However, the following stopping criteria for the number of factor to extract are currently being utilized. Let's talk about the latent root criteria. The most commonly used technique in the latent root criteria. This technique is simple to apply the either component analysis or common factor analysis. The rationale for the latent root criteria is that any individual factor should account for the variance of of at least a single variable if it is to be retained for interpretation. Which component analysis each variable contribute a value of it to the total eigenvalue. Those only the factor having latent root or eigenvalue greater than 1 are considered significant. All factor which latent root less than 1 are considered insignificant and are disregarded. Using the eigenvalue for establishing a cutoff is most reliable when the number of variable is between 20 and 50. If the number of variable is less than 20, the tendency is for this method to extract a conservative number of the factor, too few. Whereas if more than 50 variable are involved, it is not uncommon for too many factors to be extracted. Let's talk about a priori criteria. The a priori criteria is a simple yet reasonable criteria under certain circumstances. When applying it, The researcher already known how many factors to extract before conducting the factor analysis. The researcher simply instructs the computers to stop the analysis when the desired number of factors has been extracted. This approach is useful when testing a theory or hypothesis about the number of factors to be extracted. It also can be justified to attempt to replace another researcher work and extract the same number of factors that were previously found. Percentage of variance criterion. Let's talk about the percentage of variable creation is an approach based on achieving a specified cumulative percentage. So I'll talk about the percentage of variable creation. The purpose is to ensure practically significance for the drive factor by ensuring that they explain at least a specified amount of variance. No absolute threshold has been adopted for application. However, in a natural science, the factoring procedure usually should not be stopped until the extracted factor account for at least 95% of the variance, or until the last factor accounts for only a small portion, less than 5%. In contrast, in the social science, where information is often less precise, it is not uncommon to consider a solution that accounts for 60% of the total variance, and in some instances even less, as satisfactory. A variant of this criteria involves selecting enough factor to achieving a pre-specified community for each of the variables. If theoretical or practical reasons require a certain communal city for each variable, then the researcher will include as many factors as necessary to adequately represent each of the original variables. This approach differs from focusing on just the total amount of variance explained, which neglects the degree of explanation for the individual variables. Let's talk about screen test criterion. Recall that with the component analysis factor model, the later factor extracted contain both common and unique variance. Although all factors contain at least one unique variance, the proportion of unique variance is substantially higher in later factor. The screen test is used to identify the optimum number of the factor that can be extracted before the amount of unique variance being to dominate the common variance structure. The screen test is derived by plotting the latent roots against the number of uh, toads in their order of extraction, and the shape of the resulting curve is used to evaluate the cutoff point. Figure 6 plot the first 18 factors extracting in the study, starting with the first factor, or the plot slope, which I will show for next slide. The figure 6 sliply downward initially and then slowly become an approximately horizontal line. The point at which the curve first began to strengthen out is considered to indicate the maximum number of factors to extract. In the present case, the first 10 factors would qualify. Beyond 10 large a proportion of the unique variance would be including those these factors would not be acceptable. Note that in using that latent root criteria, only 8 factors would have been considered. In contrast, using the screen test provide use with 2 more factors as the general rule. The screen test result in at least 1 and sometimes 2 or 3 more factors being considered for inclusion than does the latent root criteria. Here variance among the variables. Here is a latent, root, eigenvalue criteria and screen test criteria. Heterogeneity of the respondents. So we'll talk about an underlying assumption is that shared variance extends across the entire sample. If the sample is heterogeneous about at least one subset of the variable, then the first factor will represent those variables that are more homogeneous across the entire sample, variables that are better discriminated between the subgroup of the sample. Will load on later factor many times those not selected by the criteria discussed previously when the objective is to identify factors that discriminate among the subgroup of the sample. The researcher should extract additional factors beyond those indicated by the method just discussed and examining the additional factor ability to discriminate among the groups. If they provide less beneficial indiscrimination, the solution can be run again and these later factors estimated. Summary of factor selection criteria. Let's talk about in brief. In practice, most researchers seldom used a single criteria in determining how many factors to extract. Instead, they initially used a criteria such as the latent root as a guideline for the first attempt at interpretations. After the factors are interpreted as discussed in the following selections, the practicality of the factor is assessed. Factors identified by other criteria are also interpreted. Selecting the number of factors is interrelated with an assessment of structures, which is revealed in the interpretation phase. Those several factor solution with differing number of the factor are examined before the structure is well defined. In making the final decision on the factor solution to represent the structure of the variable, the researcher should remember the considerations listed in rule of 3, which I will discuss for upcoming slide. Let's talk about one word of the quotation. In selecting the final set of factors, negative consequences arise from selecting either too many or too few factors to represent the data. If too few factors are used, then the correlation structure is not revealed and important dimensions may be omitted. If too many factors are retained, then the interpretation become more difficult when the results are rotated as discussed in the next section. Although the factors are independent, you can just as easily have too many factors as too few. By analogy, choosing the number of the factor is something like focusing a microscope too high or too low. An adjustment will obscure a structure that is obvious when the adjustment is just right. Therefore, by examining several different factor structure derived from several solutions, the researcher can compare and contrast to arrive at least representation of data. As we other aspect, the multivariates model parsimony is important. The notable exception is when factor analysis is used strictly for data deduction and the set level of the variance to be extracted is specified. The researcher should always strive to have the most representative and parsimonious set of factor possibles. Let's talk about the rule 3, choosing factor model and number of factors. Although both component and common factor analysis model yield similar result in common research setting, 30 or more variable or commonalities of 0.60 for most variables, the component analysis model is most appropriate when data deduction is paramount. The common factor model is best in well specified theoretical applications. Any decision of the number of the factor to be retained should be based on several considerations. Use of several stopping criteria to determining the initial number of factor to retain. Factor with eigenvalue greater than 1.0, a predetermined number of factor basis on research objective and the prior research. Enough factor to meet specified percentage of the variance explained, usually 60% or higher. Factor shows by the screen test to have substantial amount of common variance, that is factor before the inflection point. More factor when heterogeneity is present among sample subgroups. Consideration of several alternative solution, one more and one less factor than the initial solution to ensure the best structure is identified. Let's talk about the stage 5, interpreting the factors. Although no unique 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 unequivocal processes or guidelines determine the interpretation of the factor. The researcher with a strong conceptual foundation for the anticipated structure and its rotational has the greatest chance of success. We cannot state strongly enough the importance of strong conceptual foundation, whether it's come from prior research, theoretical paradigm, or commonly accepted principles. As we will see, the researcher must repeatedly make subjective judgment in such dimension as the number of factors which are sufficient relationship to were grouping variables, and how can these grouping be identified. As the experienced researcher can attest, almost anything can be uncovered if one try long and hard enough. For example, using different factor models, extracting different number of factors using various form of rotation. It is therefore set up to the researcher to be final at arbitrator as to from an appropriateness of the factor solution, and such decisions are best guided by the conceptual rather than empirical basis. To assist in the process or interpreting a factor structure as selecting a financial factor solution, three fundamental processes and describe within each process several subse- sub substantive issues. Factor rotating, factor loading, significance, and factor interpretation are encountered. Those after each process is briefly described. Each these process will be discussed in more detail. The three process of factor interpretation. Let's talk about the three process of factor interpretation. Factor interpretation is circular. The researcher first evaluate the initial result, then make several judgment in viewpoint and refining these results with the distinct possibility that the analysis is re-specified, requiring a return to the valuative step. Thus, the researcher should not be surprised to engage in several interrelation until an initial solution is achieved. Estimate the factor matrix. First, the initial unrotated factor matrix is computing containing in the factor loading for each variable, each factor loading are the correlation of each variable and the factors loading. Indicate the degree of correspondence between the variable and the factors, which higher loading makes the variable representative of the factor. Factor loading are the means of interpreting the role each variable play in defining each factor. Factor rotating, unrotated factor solution achieving the objective of the data reduction, but the researcher must ask whether the unrotated factor solution, which fulfill desirable mathematical requirements, will provide information that others the most adequate interpretation of the variable under examination. In most instances, the answer of this question is no, because factor analysis, a more detailed discussion following in the next section, should simplify the factor structure. Therefore, the researcher next employ a rotation method to achieve sample and theoretically more meaningfully factor solution. In most cases, rotation of the factor improves the interpretation by reducing some of the ambiguities that often accompany initial unrotated factor solution. Inter factor inter and the As a final process, the researcher evaluates the factor loading for each variable to determine the variable role and contribution. On the determining the factor structure, in the course of those e eigenvalue process, the need may arise to respecify the factor model ongoing. The deleting of variables from the analysis. The second, the desirable to employ different rotational method and interpretation. Third is that the need of extract a different number of the factors. The fourth, a desire to change from one extracting method to another. Respecification of the factor model involve returning to extracting stage for extracting factor and the beginning of the process interpretation once again. Let's talk about the rotation of factor, perhaps the most important tool in interpreting factor rotation. So most important tool, that is factor rotation. The term rotation means exactly what it implies. Specifically, the reference axis of the factor are turned about the original until some other position has been reached, as indicated either unrotated factor solution extracted factor in order of their variance extracted. The first factor tend to be journal factor with almost every variable loading significantly and its amount for the just amount of variable. The second and subsequent factor are the based on the residual amount of variance, each amount for successively similar portion of variance. The ultimate effect of rotating the factor matrix is to redistribute the variance from the earliest factor to later ones to achieving a simpler, theoretically more meaningfully factor pattern. The simplest case of rotation is an orthogonal factor rotating in which the axes are maintained of 90-degree. It is also the possible to rotate it the axis and retain the 90-degree angle between the, therefore the axis here the axis rotated with 90-degree, and when not constrained to being orthogonal, the rotation procedure is called an oblique factor rotation. Orthogonal and oblique factor rotation are depicted and the figure 7b represented. This is figure 7 which is represented orthogonal and oblique rotation. Factor rotation, the vertical axis represented orthotated factors. The second and horizontal axis represented unrotated factor. The axes are labeled with 0. The axes are labeled with 0. Original and extended outward plus 1.0 and minus 1.0. The number of the axes represent the factor loading. The first variables are labeled V1, V2, V3. Here is V1, V2 and V3. V4 and V5. The factor loading is variable. V2 is unrotated. It is determined by the drawing a dashed line horizontally from the data points to the vertically axis and factor. Similarity, a vertical line is drawn from the variable to the horizontal axis and the ortholated factor 1 to determine the loading of variable 2 on the factor 1. A similar process of following To the remain variable, determine the factor loading from the ortho rotated and the rotated solution as the played in the table 1. From the comparison purpose on the unrotated first factor, all the variable load fairly high. On the ortho related second factor, variable 1 and 2 are very high in the positive direction. Variable 5 is the moderating, high is the negative direction, and the variable 3 and 4 have considerably lower than loading negatively direction. Oblique factor rotation. Here is a ortho-related factor, orthogonal rotation factor second, ortho oblique rotation factor 3, factor variable 1, variable 2. Here is a plus variables, here is a minus variables. Oblique factor rotation. Let's talk about the comparison between rotated and unrotated factor loading. Here is a comparison between rotated and unrotated factor loading. Visual inspection of figure 7. Two lateral of variable are obvious. 1 and 2 go together and do variable 3 and 4 and 5. However, such as attending the variable is not so obvious and numerical. By rotating the original axis clockwise indicate in figure 7 the obtaining the completely different factor and diagram pattern, not the rotating of the axis and maintaining of 90 degree. The procedure of significant and factor mathematically independent and that rotation has been orthogonal. After the rotating that the factor axis variable 3 and 4 and 5 load high and factor I and variable clustering of the pattern, these variable into two groups are obvious after the rotating that the before, and even though the rotating position of the configuration and the variable remain uncharged. The same general principle of the orthogonal rotation portion of the oblique rotation. The oblique rotation method is more flexible, however, because the factor axis needed to be orthogonal, it is also more realistic because the theoretically important underlying dimensions are most assumed to be uncorrelated with each other. In figure 1 and 2 rotation method are compared. Note then the oblique rotation represent the clustering of the variable more accurately. This accuracy is also result the fact that each rotate factor axis now the closer to the representative group of variables. Let's talk about the orthogonal rotation method. In practice, the objective false method of rotation is to simplify the row and columns and the factor matrix to facilitating interpretation in factor matrix. Column represent factor, each row corresponding to a variable loading across the factor. By simplifying the row, we mean making many value in each rows and close to 0 as a possible, that is maximizing a variable loading on a single factor. By simplifying the column of, we mean making as many value in each column as close to possible, that is making the number of high loading as a few as possible. Three major orthogonal approach have been developed. First, quarter matrix. The ultimate goal of quarter matrix rotating is to simplify the row of the factor matrix. That quarter matrix focus on the rotating then initially factor so that a variable load high on one factor and as low as possible on all other factor. In these rotation, many variable can lead high or near high on the same factor because the technique centers on simplification the row. The quarter matrix method has not proved especially successful in the producing simpler structures. Its difficulty is that it tends to predict a general factor as the first factor on the which most function. All of the variable have high loading regardless of one's concept of simple structure. Inevitably, it involves dealing with the cluster or variables, a method that tend to create a large general factor. That is, quarter matrix is not in line with the goal of rotation. Varimatrix. In contrast to quarter matrix and varimatrix creations centers on simplifying the columns of the factor matrix. With the very matrix rotational approach, the maximum possible simplification is reached if there are only first and in a column. That is the very matrix method maximize the sum of the variance of required loading of the factor matrix. Recall that in quarter matrix approach, many variable can loading high or near high on the same factor. Because of the technique center and simplify the row. With the very matrix rotation approach, some high loading that is close to 1 minus plus 1 are likely are some loading near 0 in each column of the matrix. The logic is that interpretation is easier when the variable factor correlation are 1 close to either plus 1 or minus 1, those indicating a clear positive or negative association between the variable, and the factors of close to indicating a clear lack of association. The structure is functionality simple, although the quarter matrix solution is analytical simpler than the very matrix solution. Very matrix seems to be give a clear separation of the factors. In general, Kaiser experiment indicate that the factor pattern obtained by varimatrix rotation tend to be more invariant than the obtained by the quarter matrix method when the different substance of variables are analyzed. The varimatrix method has proved successful as an analytical approach to obtaining an orthogonal rotation of factors. Equimax. The Equimax approach is a compromise between the quarter matrix and varimatrix approaches. Rather than concentrating either on simplification of the row on simplification of the column, it try to accomplish some of each. Equimax has not gained whispered acceptance and is used interfrequently. Oblique rotation method. Let's talk about the oblique rotation. Are similar to orthogonal rotation except that the oblique rotation allow correlation factor instead of the maintaining independence between the rotation factor, where the several choices are available among the orthogonal approaches. However, most statistical packages typically provide only limit choice for oblique rotation. For example, SPSS provide oblique, SAS has Promax, and orthoblique, and BMDP provides DQUART and DOBLIMIN and orthoblique. The objective of simplification are comparable of the orthogonal method which the added features of the correlated factor. With the possibility of the correlated factor, the factor researcher must take additional care of validate oblique rotated factor because they have an additional ways non-orthogonality of becoming specified to the sample and not generalizable, particularly with small sample or a low case to variable ratio. Selecting among the rotational method. No specified rule have been undeveloped to guide the researcher in selecting a particular orthogonal or oblique rotation technique. In most instances, the researcher simply utilize the rotational technique provided by the computer program. Most programs have the default rotation of varimatrix, but all the major rotational methods are widely available. However, no complying analytical reasons suggest favoriting one of rotational method over the another. The choice of an orthogonal or oblique rotation should be made based on the particular needs or give research problem. To this end, several considerations in the rule thumb 4 should guide in selecting the rotational method. Judging the significance of factor loading. In interpreting factor, a decision must be made regarded the factor loading worth consideration and attention. The following discussion detail issues regarding practice and the statistical significance as well as the number of variables that affect the interpretation of the factor loading. Ensuring the practical significance. The first guideline is not based on any mathematical proportion but related more to practical significance by making a preliminary examination of the factor matrix in terms of factor loading, because factor loading is the correlation of the variable and the fact. First, the squared loading is that amount of the variable, the total variable accounted for by the action. Those the 30 loading translated to approximately 10% of explain, and the 50 loading denoted that 25% of the variance is accounted for by the factor. The loading must extended 70 for the factor to account for 50% of the variance of the variable. Those the large the absolute size of the factor loading, the more important the loading in. Rule of 4, choosing factor rotating method. Orthogonal rotation method are the most widely used rotational method. Are the performed method when the researcher goal is data reduction to either a smaller number of variables or set of uncorrelated measurement to for subsequent use in other multivariates technique. Oblique rotation method are best suited to the goal of obtaining several theoretically meaningfully factors or construct, because realistically few constructs in the real world are uncorrelated. So for upcoming video I will make the factor analysis video 3, and I will discuss further in that video. I hope this video useful for you. Thank you.